Hi, my name is Christina Otte, and I'm an undergraduate research assistant in Dr. Julian Sachs's oceanography lab. I'm presenting with my coworker, Alana Kraft. Our research focuses on the effects of glacial melting on precipitation patterns in jellyfish Lake Palau derived from hydrogen isotopes in algal lipids. We will present data supporting the idea that a southward shift of the rain bands occurred 8,200 years ago.
A catastrophic outburst of glacial meltwater into the Labrador Sea 8,200 years ago disrupted worldwide oceanic circulation for more than a century and impacted climate globally. On the present-day US and Canadian border, a massive glacier created a dam-like structure blocking glacial meltwater from moving towards the ocean. When it melted and broke, the water flooded into the North Atlantic. The introduction of such a significant amount of cold fresh water disrupted the major driving force of the ocean, thermohaline circulation. The effects of the glacial meltwater pulse are shown on the graph, where areas marked with blue circles experienced unusually colder temperatures, and those with red circles experienced unusually warmer temperatures. In order to see if this cold snap resulted in a change in climate in the tropical Pacific, we analyzed hydrogen isotopic data extracted from sediment cores in Jellyfish Lake, Palau. The isotope ratios we analyzed implied a southward shift of the tropical rain bands. Thus, our preliminary data demonstrate a trend towards a drier climate in Palau at the time of the glacial meltwater pulse into the North Atlantic.
The Republic of Palau is an archipelago of over 200 islands within the Pacific Ocean, located 8 degrees north of the equator. It is known for its heavy monsoon seasons and high climate. Palau was chosen as our area of research due to its remote, undisturbed lakes with a high rate of sediment accumulation. Its location in the tropic allows us to see how climate was altered near the equator, which drives Earth's climate systems. Palau is termed Rock Islands due to it being the remnants of an uplifted coral reef, where cracks in the rocks that formed allowed for the mixture of saltwater and freshwater, resulting in a semi-haline lake. Jellyfish Lake has a layered density gradient where less dense freshwater sits on top of the lake, while dense saltwater at greater depths results in an anoxic zone. Decaying biomass and sediment from the surface of the lake sinks to the bottom, creating a layered sequence of Earth's history. We took sediment cores from Jellyfish Lake that spanned the time of the cold snap from 8,000 BCE to 2016 CE.
For our research, we focused on deuterium, an isotope of hydrogen that contains one proton and one neutron, doubling the hydrogen atom or protium's atomic weight. Typically, the ratio of deuterium to protium, 2H1H, is reported in delta notation and compared to an international standard. If we see a greater quantity of deuterium in lakes that deviates from the average hydrogen isotope ratio, then we can conclude that the area is receiving less precipitation and experiencing a drier climate than normal. So the quantity of deuterium present in lakes provides a record of changes in past rainfall patterns. There are two processes that control lake water isotopes and their relationship to precipitation: the mixing of freshwater and saltwater, and, an occurrence coined, the amount effect. In Jellyfish Lake, the mixing between freshwater and saltwater is heightened during precipitation events. Firstly, rainwater has a lower hydrogen isotope ratio, which in delta notation means it has a more negative value, while seawater's value is defined as 0. Atmospheric water vapor and precipitation are deuterium depleted in relation to the ocean because the higher vapor pressure of atomically lighter material causes it to evaporate more readily across the globe. So, when mixing of freshwater and saltwater occurs in Jellyfish Lake, greater quantities of rainfall result in a lower, more negative delta value. The second process that governs rain and its relation to lake water isotopes is the amount effect. The amount effect is based on observations at low latitudes. As shown in this graph, regions that receive greater monthly precipitation have a lower hydrogen isotope ratio. In comparison to the Galapagos, Palau's hydrogen isotope ratio of rainwater is approximately -30 per mil, while in the Galapagos, which receives less rain, has a more enriched precipitation of about 0 per mil. So, in general, places that receive more rainfall have a lower hydrogen isotope ratio. But why is this the case? As rain falls towards the Earth, the raindrops are continuously evaporating. Lighter isotopes evaporate out more quickly. In some areas, the raindrops evaporate completely before reaching the ground. However, in areas with strong convective events, such as the tropics, precipitation occurs in large quantities very rapidly. More rain in a shorter period of time means a more humid climate, and thus less evaporation. Combine this with more mixing of freshwater and saltwater, and more rain means decreasing the hydrogen isotope ratio in Jellyfish Lake. We can't sample water from the past, but algae that grow in the lake use the hydrogen and deuterium from its water to make their lipids, or fats. So we analyzed the organic compound dinosterol. Dinosterol is produced exclusively by dinoflagellates, a taxa of photosynthetic microalgae present in Jellyfish Lake. Since this molecular fossil has the preserved ratio of hydrogen isotopes from the lake at the time the algae grew, we collected sediment in order to analyze deuterium ratios. For the collection process, we set a platform between two bows on the lake and hammered a metal pipe called a piston core down into the mud. We cut that core into 1 centimeter sections. In the laboratory, we freeze dry our sediments in order to both homogenize the sediment and allow organic solvents access to the lipid material. Next, the freeze-dried lake sediment is extracted using an accelerated solvent extractor, or ACE, in which hot solvent runs through the samples and pulls out dissolved organic compounds, much like an espresso machine. Via a saponification reaction, we free the sterols present in our samples and increase our yield. Next, we purified the dinosterol by running our samples on our HPLC, or high-performance liquid chromatography instrument, that separates compounds out via a polarity gradient. Next, having only the dinosterol present from our lake sediment samples, we perform an acetylation reaction, which improves the ability to analyze the dinosterol in our next steps by replacing the alcohol group. We can then quantify and assess the purity of dinosterol in our samples by running them on our gas chromatography instruments shown on this slide. Lastly, to analyze and quantify the 2H1H ratio within the dinosterol, we run the samples through a device that turns all of the hydrogen or deuterium into 2H molecular gas, which we then measure on our isotope ratio mass spectrometer, or IRMS, which gives us a ratio of deuterium to hydrogen.
So this is a graph of our results thus far of analyzed deuterium content of dinosterol in Jellyfish Lake. The x-axis represents the years before present as modeled by carbon-14 data. On the y-axis, we have the hydrogen isotopic composition of the biomarker as compared to a standard. And this is represented by the delta notation showing the deuterium to protium, or 2H1H ratio. So all dinosterol is much lighter isotopically than the seawater that it came from. So all of these values, as you can see, are quite negative. More fresh water in the lake will make it even lighter though. So at wetter times, the value will get more negative. Dinosterol that grew in isotopically rich water will be more enriched in deuterium and thus less negative. So values that are closer to 0 suggest a higher percentage of seawater in the lake, and therefore less rain and a drier climate. As we can see, around 8,000 to 9,000 years before present, there is a less negative value, which would mean more deuterium-enriched water in the lake, representing a period of dryness. Our lab has conducted prior research in the Galapagos Islands, which are about 1 degree south of the equator, that appear to have gotten wetter, as demonstrated by more negative values in that same period. If the Galapagos got wetter as Palau got drier, this would show a push of the equatorial band southward. Based on this work and the work in the Galapagos, it would seem likely that the large release of cold, fresh water in the northern Atlantic Ocean 8,200 years ago may have actually caused the tropical rain bands to shift south.
This climate model shows the predicted pattern of change when the ocean is subject to a large freshwater input, based on how we think the climate system responds. In this simulation, we would expect the southern tropics to get wetter, and this is exactly what our preliminary data reflects. The global effects of the glacial meltwater pulse are highlighted on this climate model, which demonstrates how Palau got drier and the Galapagos got wetter 8,200 years ago. Proven for the first time, our hydrogen isotopic data in the tropical Pacific is consistent with what climate models suggest. One glacier drastically altered global climate 8,200 years ago. Presently, glacial melting worldwide is occurring at an exponential rate due to fossil fuel emissions. With mountain glaciers such as the Greenland ice sheet melting rapidly due to anthropogenically induced climate change, it is possible that a similar disruption might occur. Our paleoclimatic data has important implications in furthering our understanding of how drastic alterations in ocean circulation could affect climate on a global scale.
So we wanted to thank our mentors, Dr. Julian Sachs and Dr. Matthew Walhow, for supervising this project and for providing us with valuable insight.
Also, thank you so much to the NSF, the UW Quaternary Research Center, and all of our funding partners for supporting our vital research. Thank you.
Thank you.